More limiting reactant problems. In this video, we're going to look at more limiting reactant situations, but here we're going to talk about which we use, the limiting reactant or the excess reactant, when trying to figure out how much of a product is going to be produced. Let's look at an example here. 1.2 grams of calcium nitrate, CaNO3. Remember, calcium would have been 2+, so it crosses over to B2. And 2.4 grams of lithium carbonate. Carbonate would have been 2, so that crosses over to the lithium, are dissolved in water. The resulting precipitate is then filtered out. So these two guys are both aqueous, and we're going to form lithium nitrate and calcium carbonate. This will be the precipitate, it'll be solid, and this is our aqueous species. Balancing, I require 2 of these, but that's all I have to do for balancing this reaction. So I got 1.2 grams of him and 2.4 grams of him. How can I figure out which one of them is going to which one of them is going to run out first? Step number 1, I have to deal with the mass of the individual particles to figure out how many particles I have. So I'll find the molar mass of these guys. Calcium is 40. And then I got 2 times nitrogen, which is 14, plus 3 times oxygen, which is 16. For a molar mass of 164 grams per mole. Here I got 2 lithiums. Lithium is 6.9. Yep. A carbon and 3 oxygens. So each particle here weighs 73.8 grams per mole. So the formula, if you like it, is N is equal to mass divided by the mass for 1 mole, or if you want to view this as a conversion, canceling out grams, introducing moles. 1 mole is 164 grams. 2.4 grams to moles. 1 mole is 73.8 grams. So 1.2 divided by 164 is 0.00732. And 2.4 divided by 73.8 is 0.0325. Those are in moles now. These guys are already in a 1-to-1 ratio, so I don't need to do anything to these. What I can clearly see is that this guy is going to run out first. So what does that mean? Well, this guy is going to limit this reaction. These products are going to be produced until this runs out. There's so much of it that it doesn't even matter how much there is. This is like if you're baking and you have 100 eggs, but you only have 1 little bag of flour. It doesn't matter if you have 100 or 200 eggs. You're going to run out of flour before you run out of eggs. So the number of eggs you have doesn't actually matter. So when predicting products, we always use the limiting reactant. So this is the product that I want to predict. He's in a 1-to-1 ratio with him. I'm going to cross out this number lightly so I can still see what it was, but so that I don't accidentally use it. I'm going to put an LR on this one. That's my little code to say that was the limiting reactant. And then I'm going to use him to predict the number of moles of him produced. But since it's a 1-to-1, I don't have to do any math here. It's 0.00732 moles, because it's 1 for every 1. Alright, I need the molar mass of this compound. Calcium was 40. Plus 12. Plus 3 oxygens at 16. So 100 grams per mole. So now, again, you can use this formula if you like the formula, but I'm kind of liking this factor reduction business, so I'm going to just treat this as a conversion. Moles, I'm canceling out moles, I'm introducing grams. So for every 1 mole I have 100 grams. So that means I'm going to get 0.732 grams of my precipitate. The rest of this is going to remain in solution because in the end the amount of calcium effectively is the ion that limited how much calcium carbonate could be produced. Let's look at one more. A sample contains 15 grams of calcium or copper 2 chloride dissolved in water. CuCl2 dissolved in water. It was copper 2, so you cross the 2 over, that's why it's copper with chlorine, with 2 chlorines. Some copper is displaced by 0.5 grams of magnesium. So magnesium was put in a solid, and the copper came out, and magnesium chloride was produced as a, I don't know what that was, as a soluble salt. I had 15 grams of this, and I had half a gram of that. Who's going to run out first? Is there going to be lots of copper chloride in that solution, or is there going to be magnesium? Now this is all 1-to-1-to-1. This is all balanced, so I don't have to worry about that. So let's find the molar mass of copper chloride. Copper is 63.6. So I'm doing molar masses now. 63.6 plus 2 times chlorine, which is 35.5. $134.6 grams per mole. And magnesium, I think, is 24.3. Yeah. Since he's an element on his own, I don't have to do any calculation there. That's that. So 15 divided by 134.6, I got 0.1114 moles of copper chloride. 0.5 divided by 24.3, I have 0.0206 moles of magnesium. Again, they're in a 1-to-1 ratio. If they weren't, I could divide by both of those coefficients to see how they actually get used up. But since it's a 1-to-1 ratio, it's very clear that this one will run out first because there's less of it. So that's my limiting reactant. I'm just going to lightly cross through that so I can still see the number, but I don't get tempted to use it. And then I'm going to use my limiting reactant to predict how much. Oh, actually the question says, how many copper ions are remaining in the solution after? Okay, so that's a slightly different question. So what I'm actually going to imagine then is that this reaction takes place and it uses up that many moles based on the displacement of the magnesium. So the question is, how much copper is left? So 0.1114 minus 0.0206, and what I'd be left with is 0.0908 moles of copper. I started with this much, I used this much initial, and this is used, and so this is remaining. The question's a little unclear here. It says how many the amount of copper ions. So I guess I could say Cu2 plus has 0.0908 moles of ions. And I could stop there. But if I wanted that in a mass, I could convert using the molar mass of copper, which is 63.55. Don't worry that it's an ion. Remember, electrons effectively don't weigh anything, so taking away electrons or adding electrons doesn't make any actual difference here. So we use the full molar mass. So I could recognize that that would be 5.77 grams. That would be the mass of the copper 2 plus ions. So you could state it in moles, you could state it in mass. I guess if the question asked, you could convert it over to the actual number of ions by using Avogadro's number. Either way, remember, limiting reactants predict how many products we get, but we can also use them to figure out how much of the reactant would be left over, or how much got used up. Just a quick note here. This came over here in a 1-to-1 ratio. Because in my chemical reaction, I was 1-to-1. Let's just suppose, for the sake of argument, that it had been 2-to-1 ratio and we had our same numbers. So I had 0.1114 to 0.0206. And I had 2 of these for every one of these. So let's call these the x's and these the y's just to keep them straight. Okay? It's important to note that to figure out how much gets used, I still need to use my mole ratio. So my 0.206 would be of y's, and if I want to convert y's to x's, I'd have a 1-to-2, and so I'd end up with 0.412 being used up. Sorry, that should be 0.0 and 0.0412. And so when I figured that out, it would be 0.0412 getting used up instead of 0.0206. So the fact that that was the same was only because the mole ratio was 1-to-1. Just because you're dealing with 2 reactants doesn't mean that you can forget to use mole ratios to predict the actual amount that reacts up or the actual amount that's produced. It doesn't make any difference. So that's just a little tip about that. And so that's how you can use the limiting reagent to predict the amount of a product. Or you can use the limiting reagent to figure out how much is remaining of the excess reagent after the reaction.